Okay, hello everybody. In this section we're going to be investigating bipolar junction transistors and talk about the phenomenon of transistor gain, which we didn't really cover too much before in the section on MOSFETs. So first we'll look at the basic structure of BJTs and then how they're connected in circuits. So the physical structure in a block diagram is three doped regions connected together. So we could have P, N doping like this, or reverse it and have P++, N plus, and then P. So these are conventionally called the NPN or PNP transistors. So the band diagram, because of the doping, looks something along these lines in normal operating conditions. So we have something very, very, very similar to what we saw in the case of the band diagram along the channel in a MOSFET. So in this case, for the NPN, we'd be looking at the electron emission from the emitter through the base and being collected in the collector. So we have the same functionality, but sort of called different things. Remember, in MOSFETs, this was called source, gate, drain. This is emitter, base, collector. Their functionalities are very similar here. So the doping diagram that produces this band diagram looks something like this. So we're going to look at the net doping in the three regions versus distance x. And in the N plus side, we're up here at 10 to the 17. The P plus side, we're at, something like 10 to the 19 for the N plus plus. Something like 10 to the 17 for the P plus, and then something like 10 to the 15 for the N side. And what I'm plotting here is ND minus NA, the net acceptor or donor doping. So the structure, although it in this writing looks symmetric, it's actually asymmetric because of this high doping here and low doping here. Switching the emitter and collector is not really the same thing. So physically, how are these laid out? In wafer fabrication, we don't actually have sort of rectangular blocks connected like this. Rather, the structure might look something like this, with an N-type epilayer grown on top of the wafer. So wafer, P plus, P plus. Some isolation regions over here. And then, sorry, I put my plus in the wrong place. An N plus region there. An N plus region here. And then a little section here of P plus. And then we would have oxide over everything here. And we have to figure out what our wires are. So this is the collector, this is the emitter, and this one here is actually the base, but look at electrically, it's connected to this P plus region, so that the order, if we look from here to here, is N plus P plus N, and then N plus again for making the ohmic contact. But really the base to collector is between here and here. So the this should be considered sort of a block diagram, whereas the physical implementation is pictured here. It's more complicated and may have different areas, different cross-sectional areas for the different junctions, resulting from the fact that it's been fabricated in a planar process. So over on this side, I've drawn a diagram of the NPN transistor, sorry, BJT transistor, connected in the common emitter configuration, which means that the emitter is connected to ground here. So we have two voltage sources. So on the left here, the voltage between the ground and the base, which means between the emitter and the base, and then the voltage CC between the emitter and the collector. So this means that these two things are not completely, these two voltages do not result in sort of orthogonal changes in this diagram. So the CC voltage affects from here to here all the way across the transistor, whereas the BB voltage only affects from here to here. But it makes it easier to keep track of the currents that we need to keep track of. So we've also drawn in a little AC source here so that we can add a VAC if we want to do so, and then amplify this, this signal using the transistor and the functionality of a voltage amplifier. So we need to keep track of these resistances on the base and collector, as well as the currents going into the base and the currents going into the collector here. But what it allows us to do, or I should say what keeping track of the voltages between the emitter and base, so we have the VBE between here and here, and the VCB between here and here. So we have the voltages that are applied to the depletion width between the emitter and base and between the base and collector. We can keep track of the relative signs of these, and on this diagram we can determine the different modes of operation. So the forward active mode is the most important one, and it's when the base emitter junction is in forward bias. So this is forward here, and then the base collector voltage is in reverse bias. So we've defined our voltage signs so that forward active ends up in the first quadrant here. Note that that means that the base collector junction here is actually reverse biased. So then if they're both in forward bias, we have the saturation region, and then cutoff will apply in this region. And then this third quadrant ends up being inverse active. So this is like flipping the emitter and collector on the junction, but things don't work symmetrically, as we pointed out before. So what we'll do next is examine the currents using this common emitter configuration, and then figure out how those currents relate to gain.